Good morning, students. In this class, I am going to teach you about a function which is analytic or not. Then, what are the conditions to find out whether the function is analytic or not? What type of equation is required to find out whether the function is analytic or not. Okay. Now, first we will see whether a function is analytic function or not. For that, first we should find out or we should know what is mean by analytic function. What is the definition for analytic function? A function is said to be analytic. That is, let it be f of z. So a function is said to be analytic at a point is at 0 in a domain D if it is differentiable not only at z0 but at every neighborhood points of z0. So this is the definition for an analytic function. A function f of z is said to be analytic at a point z0 in a domain D if it is differentiable not only at z0 but at every neighborhood points of z0. Also we should know another definition called singular point. When a point is said to be singular, the point at which the function is not differentiable is called singular point. So now we should know what is the analytic function and what is a singular point of the function. If analytic means if neighborhood points of that function should be differentiable. If it is not differentiable at a point, it is called a singular point. Okay, right. Now, to find out whether the function is analytic or not, we should use one equation called Cauchy-Reimann equation. Cauchy-Reimann equation, otherwise called as CR equations. Okay. So, to find out whether the function is analytic or not, we should use a equation to verify it called Cauchy-Reimann's equation. So, what is the Cauchy-Reimann equation? The necessary condition here, the definition for that Cauchy-Reimann is definition. The necessary condition for a function f of z is equal to u of x comma y plus iv of x comma y to be analytic in a domain D is that is the domain D, U and V satisfy the CR equations. What is the theorem? This is the definition or theorem we will tell. The necessary condition for a function f of z that is equal to u of xy plus iv of xy to be analytic in a domain D is that is the domain DUV is not in the domain DU and V satisfy the CR equation. What is the equation? Dou u by dou x is equal to dou u by dou y. This is the first Cauchy-Reimann equation. Another one is dou u by dou y that is equal to minus dou v by dou x. So these are called Cauchy-Reimann equations. If a function satisfies this Cauchy-Reimann equation, then that function is said to be analytic. Okay, so now we know what is the analytic function, what is the singular point, and what is the condition to find out whether the given function is analytic or not, and what are Cauchy-Reimann equation. Now we want to derive the Cauchy-Reimann equation. So to find out or to derive the Cauchy-Reimann equation, derivation of Cauchy-Reimann equation. So we know that now f of z that should be is equal to u of x comma y plus iv of x comma y. So according to a function is said to be analytic, it should be differentiable. So what will be the differentiation value of this equation? F dash of z that is equal to limit delta z tending to 0 f of z plus delta z minus f of z divided by delta z. Let it be equation number 1. So this is the main equation. Now we want to find out what is the value of z, what is delta z, then we substitute, then what is the function of z plus delta z. If substitute this value, then we solve, we will get the Cauchy-Reimann equation. Okay, now we will see one by one. Now let us consider z is equal to x plus iy. Okay, now f of z is equal to u plus iv. Then so this u is nothing but the function of x comma y. Similarly, the function of v is the function of x comma y. Okay, now find out delta z. So we know z is equal to x plus iy. So delta z is equal to delta x plus I delta y. Now z plus delta z, you add these two, this also. So z is equal to, we know, x plus iy, then delta z is equal to delta x plus I delta y. Then now separate the real and imaginary part. Now separate real and imaginary part. Then what we will get, that is equal to x plus delta x plus I y plus I y plus delta y. Okay. Now you find out f of z plus delta z. We know z, we know delta z, we know z plus delta z, we know. So now substitute the value. So what will we get? U of here, u of x plus delta x, y plus delta y plus IV into x plus delta x, y plus delta y. Okay. So we know x, then we calculating what is delta x. We know f of z is equal to u plus iv, then we are making it in terms of x comma y, therefore u of x comma y plus iv x comma y. Then we are substituting that value, then we are getting f of z plus delta z is equal to u of x plus delta x, y plus delta y plus iv of x plus delta x, y plus delta y. Okay, now substitute these values in equation 1. Therefore, equation 1 becomes f dash of z, that is equal to limit delta z tending to 0 f of z plus delta x, delta z f plus delta z minus f of z divided by delta z. This is equation number 1. I am again writing here. Now it becomes limit delta z tending to 0. Now substitute this value. U of, that is this value, u of x plus delta x, y plus delta y plus iv of x plus delta x, comma, y plus delta y. This is the f of z plus delta z, we can write. Then minus value of f of z. F of z is this, that is u of x comma y plus iv of x comma y divided by, what is the value? Delta z. You make it delta z. Otherwise you will make it delta z also delta x plus I delta y. Okay. Now separate real and imaginary part. Now separate real and imaginary part. Okay. So what we will get? F dash of z, that is equal to limit delta z tending to 0 u of x plus delta x, y plus delta y minus u of x comma y plus I into v of x plus delta x, y plus delta y minus v of x comma y divided by delta x plus I delta y. Okay. Now there are two conditions occurs. One is, case 1 is along x-axis what is the value of f dash of z. Then another condition is what is the value of f dash of z along y-axis. So two cases we want to derive. What is the value of f dash of z along x-axis and what will be the value of f of z along y-axis. Okay, so first case, that is here two cases. One, case 1, it should be f of z is along x-axis. Another case is f dash of z is along y-axis. Okay, so for these two cases we want to calculate the value. Now for that, first we will consider f dash of z along the x-axis. F dash of z along the x-axis, that is case 1. Consider f dash of z along x-axis. For that we will draw a small diagram, then you will easily understand the things. Now you divide x-axis and y-axis. This is along the x-axis and this will be the y-axis. Okay, this we know. Now consider a neighborhood points, maybe here, 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 like that. So this is x-axis, the points are also in the x-axis. So this is along x-axis, so what will be the value? Now when along x-axis y points are fixed, okay? When we are going along x-axis, y points are fixed. That means delta y equal to 0. Now we know delta z is equal to delta x plus I delta y. When delta y becomes a 0, delta z is equal to what? Delta x. Therefore, when delta z tending to 0, automatically delta x is also tending to 0. Okay. So now you apply this condition here. That is, we know the earlier equation, we know this earlier equation, this equation, that is f dash of z is equal to limit delta z tending to 0, this equation. In this equation, we will apply the condition now. In this equation, now we will apply the condition. So when you are applying the condition, what it happens? So f dash of z, that is equal to limit instead of delta x you make it now delta x, okay, 0, then u of x plus delta x, we know the another that equation, what is the value? Y plus delta y, but delta y is 0, therefore it becomes y only here, minus u of x comma y plus I into v into x plus delta x comma y plus delta y is 0, again the term becomes 0, so y minus v of x comma y divided by delta x plus I delta y is 0, therefore the remaining term is only delta x. Now you see all the terms in the delta x only. Now limit delta x tending to 0, u of x plus delta x comma y minus u of x comma y divided by delta x. Sorry, here y term is also there. No? I missed the term. You see, that is limit delta x tending to 0, u of x plus delta x comma y minus u of x comma y plus I v of x plus delta x comma y minus v of x comma y whole divided by delta x. Now separate the terms with delta x, separate the terms with real part and imaginary part. So limit delta x tending to 0, u of x plus delta x comma y minus u of x comma y divided by delta x. This is one part. Then another part is I limit delta x tending to 0, v of x plus delta x comma y minus v of x comma y whole divided by delta x. So I have divided this equation into real part separately and also imaginary part separately. Okay. But this above equation, this equation looking like another common equation. You see that what is that equation? It is looking like the equation f dash of x is equal to limit h tending to 0 f of x plus h minus f of x divided by h. You see, limit tending to 0 f of x plus h. Here f of x plus h means x plus delta x delta y, that is y, minus f of x, that is f divided by h. So this equation is similar as this equation. Okay, now this equation represents the partial differential equation as x changes to delta x but y is constant. So in this condition, what we have made, when along the x-axis y should be a constant, so it should be considered as a partial differential equation. It should be considered as a partial differential equation because this is all terms are changed in the form of delta x. We removed the delta y terms. So it is similar as the below equation, and it means that it represents the partial differential equation. That is, the above equation represents the partial differential equation as x changes to delta x but y is constant. Okay, so the above equation is looking like this equation f dash of x is equal to limit h tending to 0 f of x plus h minus f of x divided by h, and also the above equation represents the partial differential equation as x changes to delta x but y becomes 0 or constant. Y becomes a constant. When constant is differentiated, that value becomes a 0. We know that things. Now, therefore, this equation, the above equation, be changed as f dash of z that is equal to dou u by dou x plus I dou v by dou x. So since it is the partial differential equation, the above equation will be changed as dou u by dou x plus I dou v by dou x. How it comes? This is similar as this equation. The solution of this equation will be, actually the solution of this equation will be in terms of x only, not in the terms of y. Therefore, f dash of z is equal to dou u by dou x plus I dou v by dou x. Let this equation A. Let this equation be A. Now, we apply the another condition, that is f of z is along y axis. Now, case 2. Consider f dash of z is along y axis. Similar way we should draw a diagram, that is this is x axis, y axis. Now x values are constant, only y values are changing. That is, when along y axis x is constant, therefore delta x is equal to 0, delta z is equal to delta x plus I delta y. Since delta x is 0, delta z is equal to I delta y. When delta z tending to 0, then delta y also tending to 0. So same. Now apply this in the earlier equation. What we will get? F dash of z that is equal to limit delta y tending to 0 u of x plus delta x is 0, therefore y plus delta y is remaining minus u of x comma y plus I into v x y plus delta y minus v of x comma y whole divided by I into delta y. Instead of delta z, we will make it I delta y. Now, limit. Now you change a real part and imaginary part separately. So delta y is equal to u of x comma y plus delta y minus u of x comma y divided by I delta y. Similarly, plus limit delta y tending to 0 I v of x y plus delta y minus v of x comma y whole divided by I into delta y. Now this I and this I will be cancelled. Delta y will be cancelled. Now you take this I separately. This I separately outside. So 1 by I limit delta y tending to 0 u of x comma y plus delta y minus u of x comma y plus limit delta y tending to 0 v of x y plus delta y minus v of x comma y divided by delta y. Here also I missed delta y. This is delta y. Okay. Therefore, it is similar as partial differential equation. In this equation, x terms becomes a constant, only y term is there. Therefore, this is called as a partial differential equation. Hence, this above equation be written as f dash of z, that is equal to 1 by I dou u by dou y plus dou v by dou y. So, this is the second equation we got. So we got already this is the equation A. F dash of z is equal to dou u by dou x plus I dou v by dou x. Then when I applying the case 2, condition 2, then I am getting f dash of z is equal to 1 by I dou u by dou y plus dou v by dou y. Now equate these two equations A and B. Equate A and B. So, dou u by dou x plus I dou v by dou x, that is equal to 1 by I dou u by dou y plus dou v by dou y. Okay. Now, therefore, we will get now dou u by dou x plus I dou v by dou x, that is equal to minus I dou u by dou y plus dou v by dou y. That is 1 by I, it will be written as 1 by I will be written as minus I. Therefore, minus I dou u by dou y plus dou v by dou y. Now, compare the real and imaginary parts. Compare real and imaginary parts. So, we will get dou u by dou x, that is equal to dou v by dou y. This is one equation. Then dou v by dou x, that is equal to minus dou u by dou y, or dou u by dou y, that is equal to minus dou v by dou x. This is another equation we are getting. So this is equation number 2. These 1 and 2 equations are called as Cauchy-Reimann equations. Therefore, Cauchy-Reimann's equation is dou u by dou x, that is equal to dou v by dou y, dou u by dou y is equal to minus dou v by dou x. So, this is the derivation of Cauchy-Reimann's equation. So, a function is given. If we want to find out whether the function is analytic or not, we should find out these values. So, whether that equation whether the function satisfies this Cauchy-Riemann equation, then the function is said to be analytic. Okay. So what is the Cauchy-Reimann equation? Dou u by dou x is equal to dou v by dou y. Similarly, dou u by dou y is equal to minus dou v by dou x. So these are the sufficient conditions. Otherwise, it is called as sufficient conditions. Sufficient conditions. So sufficient conditions for a function to be analytic is it should obey CR equation. Also, this dou u by dou x, dou v by dou y, dou u by dou y and minus dou v by dou x should be continuous. So this is the two main sufficient conditions for a function to be analytic. Okay, so in this class we saw what is the analytic function, what is the definition for an analytic function, then what is Cauchy-Reimann equation. So whether the function satisfies this Cauchy-Reimann equation, then that function is said to be analytic, and we derived Cauchy-Reimann equations. Okay, hope you will all understand this topic. I will meet you with next topic in the next video. Thank you.